Hello, my name is Renita.
I'm Satish.
And I'm Miguel.
I would like you to think about this question. What is necessary for daily life, electric, and goes on and on? Here's a hint. They make up the building blocks of life. They are charged and made up of repeating units much like polymers. It's a polyelectrolyte. Polyelectrolytes are found everywhere in modern life. Our DNA is a polyelectrolyte. It's used as soaps, shampoos, and cosmetics. Even the exoskeletons of crustaceans are polyelectrolytes.
But before we go into depth about polyelectrolytes, we should understand what are polymers. So polymer is a Greek word, poly means many and mers meaning units. So polymer is a large molecule made up of repeating subunits. But now the question is, how is this polymer structured, or how does it look like? The following clip from study.com created by Nathan Prefford answers this question a bit more in depth. The structure of a polymer is visualized by imagining a chain. The chain has many links connected together. Similarly, the monomers, or the repeating units, in a polymer are bonded to each other to form a polymer chain.
Now, what is the difference between a polyelectrolyte and a polymer? A polyelectrolyte is a type of polymer, but in this case, each monomer has the capability of being charged. This special property allows these large molecules to be negatively or positively charged, and be soluble in polar solvents such as water. Many interesting applications and materials arise from the properties of polyelectrolytes. Renita will now give a rundown of the history of polyelectrolytes.
To begin, we'll discuss some of the major research that has been done on polyelectrolytes. This is a fairly new topic of research.
The earliest polyelectrolyte research dates back to the 1930s, when Hendrik Gerard Buitenberg de Jong and his co-workers at the University of London examined the interactions of hydrophilic or water-loving polymers in an aqueous solvent, also known as a water-like solvent. They discovered that some of these polymers contain ionizable functions or electrolytes. They had the ability to co-react with one another to form phases containing more polymer and less water than the total solution. These polymers were called polyelectrolytes. These co-reactions generally only occurred with two polyelectrolytes with opposite signs. These co-reactions were sensitive to temperature, pH, and iodic strength. Due to unresolved questions of these sensitivities, polyelectrolytes are highly researched. In 1949, Piso and Sadak made the first reported study on the interactions between strongly acidic polyanions. Prior to this report, most research was done over weakly basic and weakly acidic polyanions. They found that the reaction between two polyelectrolytes created a colloid precipitant rather than a gelatinous phase that had been studied previously. The reactions occurred rapidly and was essentially stoichiometric. In the 70s, Michel Armand began to research polymers because soft electrolytes would be preferred to hard ceramics for electrodes. In 1978, he was able to show the technological importance of these new materials for storage energy devices. Taking an interest in lithium-ion batteries, which contain a polymeric film and have the possibility of using polyelectrolytes as a source of energy, he was able to establish the electrical properties of polymer salt complexes formed within the lithium and suggested that it should be a power source for electric cars and could be ultimately used as an alternate source of energy, much like wind power and solar power. In 1982, Charles F. Anderson and M. Thomas Recker Jr. from the Department of Chemistry at the University of Wisconsin published a paper in the Annual Review of Physical Chemistry titled Polyelectrolytes Theories and Their Applications to DNA. The team first questioned if DNA behaved like other cylindrical polyions, then did a careful statistical analysis of the Poisson-Boltzmann and the counter-ion condensation theories and compared them to previously known polyelectrolytes. They discovered that the thermodynamics, kinetic, hydrodynamic, and molecular properties of DNA is similar to rod-like polyions. This meant that biological material such as DNA behaves like other polyelectrolytes and has predictable properties. Speaking of predictable properties of polyelectrolytes, Miguel is now going to talk about the thermodynamics of polyelectrolyte solutions.
Thank you, Renita. For polyelectrolyte solutions, we are interested in understanding the interactions of polyelectrolytes at the molecular level to be able to understand the phenomena that occurs at the macroscopic level. Thermodynamics helps us with this. Thermodynamics is the study of energy conversions or energy transfer into or out of a system and its effect on the physical properties of the system. For example, thermodynamics allows us to predict the states of matter. It also lets us generalize complicated systems such as an engine. In chemistry, it allows us to predict how a reaction will occur, if it will occur at all, or even how much energy we need to get it started. Additionally, it also tells us the nature of mixtures and solutions, which is of particular importance when it comes to understanding polyelectrolytes. Now I will give a quick overview of general thermodynamics. We have the first law of thermodynamics, which states that energy cannot be created or destroyed. Next, we have the internal energy U, which is a state variable because it doesn't depend on the path taken. It only depends on the initial and outlet conditions. This is given by the change in internal energy equal to the heat input into the system minus the work done by the system. And again, is the energy change within the system. Next, we have the enthalpy, which is also a state variable, and it not only quantifies the internal energy, but it also quantifies the work done by a change in pressure or volume, otherwise known as flow work. Next, we have the entropy, which is a measure of the disorder in the system. To think of entropy, we must think of how the energy spreads out in a system or has configurations. In general, a system that has a perfect configuration there's only one way to have that, but an infinite number of ways to have a disordered configuration. This gives rise to the second law of thermodynamics, which states that the universe is always going to chaos. In other words, the entropy always increases. This explains why ice melts at room temperature, as it can be seen here in this diagram, because the solid wants to increase its entropy, so it's turning into a liquid where the molecules have more room to move. Using the enthalpy and the entropy, we get the Gibbs free energy, which tells us the amount of free energy in the system. If we have a negative amount of free energy, that means that a system will happen spontaneously, meaning that it doesn't require any more energy input. But if it's positive, that means that it requires an energy input to occur. This chart summarizes the different effects on the Gibbs free energy based on the enthalpy and the entropy. But in general, our polyelectrolyte solutions, if they have a negative delta G, that means that they are miscible, which is really important in polyelectrolyte solutions. So why is this important? Why do we care about the thermodynamics of polyelectrolyte solutions? Well, it allows us to predict behavior of polyelectrolytes. It also allows us to predict the physical properties in solutions, which is very important in chemical processing. It also allows us to have new applications, such as emulsions, surfactants, and even superabsorbent materials. Before going into the thermodynamics of polyelectrolyte solutions, we must understand the difference between the polymer and polyelectrolyte thermodynamics. First of all, polymers are large hydrophobic molecules, which means they are not generally miscible in water, while polyelectrolytes are large charged molecules in solutions. This means that they can be in polar solvents such as water. This charge interaction is the main difference between the polymers and polyelectrolyte thermodynamics. There have been many attempts to describe the thermodynamics of polyelectrolyte solutions, but here I will describe a few of the most prominent theories that have provided a good understanding and starting point to new and better models. First, we have the Boltzmann-Poisson distribution, which describes how electric potential is distributed around a system. In the case of polyelectrolytes, knowledge of how the charges distribute allows for predictions of how the attractive forces are around the polymer and how this affects the overall thermodynamics. But this model is a generalized electric potential distribution, which makes it a little hard to pinpoint it for polyelectrolyte solutions. Due to this complexity, the Debye-Huckel theory was developed to ease in the prediction of these electric potentials. The approximations made a simplification of the Boltzmann-Poisson distributions, but this theory was useful for single charge molecules, but it didn't describe very well the polyelectrolyte solutions. So the Manning model was developed, which built upon these last two models and theories, but the main difference in the assumption was that the polyelectrolytes were modeled as long cylindrical line charges. And additional assumptions were made, but this allowed this model to predict some very interesting behaviors of polyelectrolyte solutions. Particularly, it was very good at catching the differences between a diluted polyelectrolyte solution and a concentrated polyelectrolyte solution. All these models are used to predict the thermodynamics properties that allow us to understand polyelectrolytes at a more fundamental level. Satish will now go more in depth about the polyelectrolyte chain dynamics.
So after learning about thermodynamic aspect, let's dig a little bit into chain dynamics of polyelectrolyte solutions. First of all, what is chain dynamics and why do we care about it? Chain dynamics in general refer to what shape or conformation a polymer chain can take. We care about the conformation that a polymer chain can take in solutions because that determines the volume occupied by polymer in solution, which in turn relates to viscosity of the polymer solution. And we all know that viscosity is an important property to know for an engineer of a polymer processing industry. So, what decides these conformations? Well, the obvious answer could be the interactions of polymer molecule in solutions. But what kind of interactions could exist in solution? Well, either polymer interactions with its own molecule or with the solvent molecule could exist. So, in general, we can say that a polymer conformations are dependent on polymer-solvent pair, and based on these interactions, the polymer chain can take any shape. Before talking about polyelectrolyte chain dynamics, we look into how neutral polymers behave with different kinds of solvents. Generally, solvents can be categorized into two types, good and bad. As the simple name suggests, when you mix a polymer in a good solvent, polymer-solvent interactions dominate. When if you consider the other type of solvent, polymer-polymer interactions dominate and hence the solvent is called a bad solvent. In a good solvent, the polymer takes the conformation as shown in the figure. The blue balls correspond to monomers and the green balls correspond to solvent molecules. Due to dominant polymer-solvent interactions in a good solvent, the polymer chain tends to be surrounded by more solvent molecules from all sides. This will create a screening effect for other monomers, which tend to approach this molecule. Hence, the region occupied by solvent is inaccessible to other monomers, which is called the excluded volume effect. So this means the two monomers can never intersect each other. This conformation was called a self-avoiding walk by Werner Kuhn in 1934. But for bad solvents, polymer molecule tends to be surrounded by more other polymer molecules, and hence they collapse into a globule as shown in the figure. Well, now we'll look at some animations to understand these conformations. These video clips show the molecular dynamic simulation of self-avoiding walks of a polymer in a good solvent. Now, you might have played this cool game called Snake Xenia, which was a unique feature of old Nokia mobile phones. This game goes on as long as the snake doesn't touch itself. Similarly, the same rules apply to self-avoiding walk, where two monomers do not intersect. In this video, the polymer takes a globule conformation in bad solvent, which is represented by a reddish background. And as the solvent becomes good, it takes an extended conformation, that is self-avoiding walk, and moves freely in solvent. The purple background represents the good solvent. Now that we know about the interactions in a polymer solution, let's talk about how these interactions contribute to overall potential energy of the system. In the 40s, the Fleury-Huggins theory was developed for neutral polymers to understand the same. This is a lattice model theory where either a polymer or a solvent molecule can occupy each lattice site as shown in the image. The white cells refer to solvent molecules and the colored cells refer to polymer molecules. The left-hand side of the image represents polymer in a good solvent, where polymer-solvent interactions dominate, and polymer chains move freely in solvent. But whereas the right-hand side of the image represents the polymer in a bad solvent, where polymer-polymer interactions dominate and polymer molecules stick to each other. The energy of the system is described by its conformational energy, which are mainly due to polymer-solvent, polymer-polymer, and solvent-solvent interactions. But for polyelectrolyte solutions, apart from conformational interactions, electrostatic interaction exists as well. They could be either between two charged monomers or a charged monomer and free ions in solution. These free ions in solution are called as counterions. Because of these added interactions, the polymer chain shows no longer a self-avoiding work configuration in good solvent. So now we'll see how these added interactions affect the chain conformations for dilute polyelectrolyte solutions. First, let's talk about the interactions in a dilute polyelectrolyte solution. In dilute solutions, the polyelectrolyte chains are far apart, and therefore the interactions between chains is negligible when compared to intra-chain interactions. In a dilute salt-free solution, the concentration of counterions is very low and are uniformly distributed in solution. Hence, polymer counterion interactions are not significant. From the understanding of forces on the polyelectrolyte chain, you can compute the potential energy of the system. This equation describes the potential energy of a polyelectrolyte chain in general. As of now, we understand only the contributions of different terms in the equation, but we do not go into depth of them. The first term on the right-hand side is due to conformational energy. The second term accounts for electrostatic interactions, and the third term is due to short-range interactions between monomers. So the first one is based on a Flory-like approach for polyelectrolyte chains, which was developed by Kern and co-workers in 1948. Some of the drawbacks in this model were addressed by the scaling model, which was developed by Nobel laureate De Gennes in 1976. De Gennes was a French physicist and received Nobel Prize in Physics in 1991. In Flory theory, the conformational and electrostatic energy primarily contributes to system's potential energy. The short-range interactions between monomers is neglected. Both conformational and electrostatic energy vary with end-to-end distance. The conformational energy increases with increase in end-to-end distance, whereas electrostatic energy decreases with increase in end-to-end distance. Any system will try to reduce this potential energy. Therefore, the chain will take a conformation with end-to-end distance Re such that it reduces the potential energy of the chain. In scaling model, De Gennes described the polyelectrolyte in solution as a chain of electrostatic blobs containing monomers. According to this theory, on length scale lower than that of blob size, the conformation of the chain is unperturbed, which means there is no interaction of monomers inside the blob and therefore the chains behave ideally. But on the length scale larger than blob size, electrostatic interactions dominate and the blobs repel each other, thus fully extending the polyelectrolyte chain into an array of blobs. The end-to-end distance according to this theory scales as given in the equation, where B is the bond length and N is the degree of polymerization. But the forces on all blobs are not the same, and hence they should be of different lengths. The blob in the middle experiences more interactions compared to blobs at the chain ends. So this decreases the blob size near center of the chain, leading to non-uniform stretching of polyelectrolyte chain. In 2003, Leo calculated end-to-end distance for non-uniform stretching of polyelectrolyte chain using molecular dynamic simulations. He found that end-to-end distance scales as given in the equation. Now, this equation is similar to the one that was obtained by Flory approach. So we can say that the logarithmic term accounts for the non-uniform stretching of the polymer chain. So far, we have discussed about history of polyelectrolytes, some thermodynamic models, chain dynamic of neutral polymers in different solvents, and chain dynamics of dilute polyelectrolyte solutions. Before moving on to applications of polyelectrolytes, I would like to show you a video clip. So far, the discussion was restricted to salt-free solutions, but this video would demonstrate the effect of added salts on the chain dynamics. So, in this video, 1 gram of sodium polyelectrolyte is mixed with 200 ml of water, and this results in formation of a highly viscous solution, as shown in the video clip. But when few grams of salt is added to this solution, the viscosity falls down and the solution behaves as a normal solution. Now, can you guys guess why this happens? Well, I could give you an hint. It is related to the basic difference between a neutral polymer and a polyelectrolyte.
There has been almost 100 years of research into polyelectrolytes. There are several things in our daily lives that are considered polyelectrolytes, such as the exoskeletons of crustaceans, even our own DNA and RNA, and proteins. Polyelectrolytes are both synthetic and organic. They are used in oil recovery by changing the surface tension of the water, which is demonstrated by the Norzarex in the following video, to display their new product Norzarex APX powder and pad. The first example shows 800 milliliters of gasoline is poured into an aquarium of drinking water to simulate groundwater contamination. To absorb the gasoline, Norzarex APX pad with 80 grams of certified polyelectrolyte solution is on top of the gasoline contamination. To simulate a beach that has been contaminated by crude oil, 1,000 milliliters of crude oil is poured on top of the sand and sea system in the aquarium. To absorb the crude oil, 100 grams of Norzarex APX powder, again polyelectrolyte solution, is added on top of the oil. The reaction takes place within minutes, but it takes 24 hours to completely solidify. First, we will look at the gasoline absorbed by the Norzarex APX pad. You will see that all the gasoline has been contained by the pad, and there's a clean surface on the drinking water. Next, we will look at the crude oil. You will see that we've created a removable skin that leaves nothing but the sand and sea. Polyelectrolytes are used in wastewater treatment through a process called flocculation. The following video from Chimera will show how polyelectrolytes are used in wastewater treatment. These are samples of industrial wastewater. Polyelectrolytes are added to the water as a diluted solution. As the solution is mixed, small particles grow into larger particles and can be easily separated. This process is called flocculation. The water can then be recycled to the plant or be put back into nature. And the solids that remain are called sludge. Polyelectrolytes are even used in our homes to create bubbly soaps, shampoos, and even cosmetics. The following videos from Silverson Machines stars the Silverson mixer, but also shows the importance of surfactants, another form of polyelectrolytes in cosmetics. In order to create a basic cosmetic, the oil phase is first prepared and any solid waxes are melted. The aqueous phase is then prepared with a high shear energy mixer. Thickening and emulsifying agents are then added, such as polymers. The oil is then added to the aqueous phase immediately to create an emulsion. The polyelectrolytes previously added, or surfactants, allow for the water and oil phases to combine. The high shear mixer then allows for the emulsion to have a smooth consistency. We hope that you have a better understanding of the physics and thermodynamics of polyelectrolyte solutions, as well as their uses in the modern day world.
By the way, did you guys figure out the answer for the question which I asked you before? Well, it's really simple. When the salt is added to a polyelectrolyte solution, the salt ions neutralize the charge on the monomer. Hence, the chains are no more in elongated conformation. Thus, the polyelectrolyte behaves like a neutral polymer and the volume occupied by the chain decreases, thereby decreasing the viscosity.
Now, we would like to thank you for taking time for watching our video. Bye.
Goodbye.